When dealing with paralleled conductors, ensuring the correct sizing of the equipment grounding conductor, or EGC, is crucial for safety and code compliance. Let's address a scenario involving a 225 amp feeder with 4/0 conductors that are paralleled. The initial setup involves a 4/0 conductor coming from a circuit breaker into a junction box. At this junction box, the conductor splits into two sets of parallel 4/0 conductors, each set run in separate 2-inch metal raceways. This parallel configuration extends for approximately 300 feet, where the conductors are then combined back into a single set of 4/0 conductors in another junction box before terminating at a disconnect. Initially, a number 4 equipment grounding conductor is installed where there is a single set of 4/0 conductors. The contractor installed a single number 4 in each of the paralleled raceways, believing this to be compliant with NEC sections 250.122b and 250.122f, reasoning that 2 times the size of the number 4 is equivalent to 2 number 4s. However, this interpretation is incorrect. According to the National Electrical Code, specifically section 250.122b, when multiple conductors are paralleled, the equipment grounding conductor must have a cross-sectional area no less than the largest equipment grounding conductor connected to any of the paralleled conductors. In this case, with 4/0 conductors being paralleled, the equipment grounding conductor in each raceway must be a number 1 American wire gauge, AUG. Further, NEC section 250.122f stipulates that when multiple equipment grounding conductors are installed in parallel, they shall be of the same size, unless otherwise required by 250.122b. Therefore, both parallel raceways should contain a number 1 equipment grounding conductor. The contractor's interpretation, suggesting that the combined cross-sectional area of 2 number 4 equipment grounding conductors meets the requirement for a single number 1 equipment grounding conductor, is a misinterpretation of the code. The code requires a single conductor of the appropriate size in each raceway. To summarize, the equipment grounding conductor in each of the parallel raceways must be increased to a number 1 to comply with NEC section 250.122b. This ensures adequate grounding capacity for the paralleled conductors, providing a safe and compliant electrical installation. This is how to correctly size the EGC, or equipment grounding conductor, in parallel raceways per NEC 250.122b. To further elaborate on the NEC requirements for equipment grounding conductors, it's beneficial to delve into some of the specifics outlined in Article 250 of the National Electrical Code. Article 250 provides comprehensive guidelines for grounding and bonding electrical systems to ensure safety and minimize the risk of electrical shock. Firstly, let's consider the purpose of equipment grounding conductors. Equipment grounding conductors are designed to provide a low impedance path for fault current to return to the source. This low impedance path facilitates the operation of overcurrent protective devices such as circuit breakers or fuses, which quickly disconnect the circuit in the event of a ground fault. Without an adequately sized equipment grounding conductor, fault current may not be sufficient to trip the overcurrent device, leading to prolonged exposure to dangerous voltage levels and increased risk of electrical shock or fire. Now let's focus on the specific requirements for equipment grounding conductors in parallel installations. As previously mentioned, NEC section 250.122b addresses the sizing of equipment grounding conductors for parallel conductors. The key principle here is proportionality. The equipment grounding conductor must be sized proportionally to the size of the phase conductors. This ensures that the grounding path has sufficient capacity to handle the available fault current. In the scenario described, where 4/0 conductors are paralleled, the code mandates the use of a number 1 equipment grounding conductor in each raceway. This requirement is based on the ampacity and fault current carrying capability of the 4/0 conductors. A number 1 equipment grounding conductor provides the necessary capacity to safely handle fault currents associated with the parallel 4/0 conductors. It's important to note that the code does not allow for the summation of multiple smaller equipment grounding conductors to meet the requirement for a larger conductor. Each raceway containing parallel conductors must have its own appropriately sized equipment grounding conductor. This ensures that each parallel path has a dedicated grounding path, minimizing impedance and maximizing fault current carrying capability. Furthermore, NEC Section 250.122F emphasizes the importance of maintaining consistent sizing of equipment grounding conductors in parallel installations. This section states that when multiple equipment grounding conductors are installed in parallel, they must be of the same size, unless otherwise required by 250.122b. This provision aims to prevent imbalances in fault current distribution among the parallel grounding paths. By ensuring that all equipment grounding conductors in a parallel installation are of the same size, the code helps to promote uniform current sharing and minimize the risk of localized overheating or failure. In addition to these specific requirements, it's essential to consider other factors that may influence the sizing of equipment grounding conductors. These factors include the length of the circuit, the type of raceway used, and the available fault current at the source. Longer circuits may require larger equipment grounding conductors to compensate for increased impedance. Similarly, certain types of raceways may have higher impedance than others, necessitating adjustments to the equipment grounding conductor size. The available fault current at the source is another critical factor to consider. Higher fault currents demand larger equipment grounding conductors to ensure adequate fault current carrying capability. To determine the appropriate size of equipment grounding conductors, it's necessary to perform calculations based on the specific characteristics of the electrical system. These calculations typically involve determining the available fault current, the impedance of the circuit, and the allowable voltage drop. Electrical engineers and qualified electricians use specialized software and tools to perform these calculations accurately and efficiently. It's also worth noting that the NEC provides tables and guidelines to assist in the selection of equipment grounding conductors. These tables specify the minimum size of equipment grounding conductors based on the size of the phase conductors and the rating of the overcurrent protective device. While these tables provide a convenient reference, it's essential to understand the underlying principles and perform calculations to ensure that the selected equipment grounding conductor is appropriate for the specific application. In conclusion, correctly sizing equipment grounding conductors in parallel installations is essential for ensuring electrical safety and complying with the National Electrical Code. NEC Sections 250.122b and 250.122f provide specific guidance on the sizing and installation of equipment grounding conductors in parallel systems. By adhering to these requirements and considering other relevant factors, electrical professionals can design and install electrical systems that minimize the risk of electrical shock and fire. Furthermore, regular inspection and maintenance of equipment grounding conductors are crucial to ensure their continued effectiveness. Over time, corrosion, damage, or loose connections can compromise the integrity of the grounding path, reducing its ability to safely carry fault current. Therefore, it's essential to periodically inspect equipment grounding conductors for any signs of deterioration and to promptly repair or replace any damaged components. In addition to complying with the NEC, it's also important to follow industry best practices for grounding and bonding. These practices may include the use of supplemental grounding electrodes, bonding of metallic enclosures, and proper termination techniques. By implementing these measures, electrical professionals can enhance the overall safety and reliability of electrical systems. Finally, it's worth emphasizing the importance of ongoing education and training in the field of electrical safety. The NEC is updated regularly to reflect advancements in technology and changes in industry practices. Therefore, it's essential for electrical professionals to stay informed about the latest code requirements and best practices. Continuing education courses, seminars, and workshops provide valuable opportunities to learn about new developments in electrical safety and to enhance technical skills. In summary, correctly sizing and maintaining equipment grounding conductors in parallel installations is a critical aspect of electrical safety. By understanding the NEC requirements, following industry best practices, and staying informed about the latest developments in the field, electrical professionals can ensure that electrical systems are designed and installed to provide a safe and reliable source of power. Now, let's consider some specific examples of how these principles apply in real-world scenarios. Imagine a large commercial building with multiple electrical panels serving various loads. In this building, it's common to have parallel feeders supplying power to the panels. To ensure adequate grounding, each parallel feeder must have its own appropriately sized equipment grounding conductor. For instance, if a panel is fed by two sets of parallel 500 kc mil conductors, each set must have a corresponding equipment grounding conductor sized according to NEC section 250.122b. Depending on the ampacity of the 500 kc mil conductors and the available fault current, the equipment grounding conductor in each raceway may need to be a number 1/0 or larger. Similarly, in an industrial facility with heavy machinery and equipment, parallel conductors are often used to supply power to high-demand loads. In these applications, it's crucial to carefully calculate the required size of the equipment grounding conductors to ensure that they can safely handle the available fault current. Factors such as the length of the circuit, the type of raceway, and the grounding impedance of the equipment must be taken into account. In some cases, it may be necessary to use oversized equipment grounding conductors to provide additional fault current carrying capacity. Another common scenario where parallel conductors are used is in underground distribution systems. In these systems, multiple conductors are often run in parallel to increase the ampacity of the circuit and reduce voltage drop. To ensure proper grounding, each parallel conductor must have its own dedicated equipment grounding conductor. The size of the equipment grounding conductor must be determined based on the size of the phase conductors and the characteristics of the soil in which the conductors are buried. In addition to these examples, there are many other situations where parallel conductors are used in electrical systems. In each case, it's essential to carefully consider the NEC requirements and industry best practices to ensure that the equipment grounding conductors are properly sized and installed. Remember, the primary goal of equipment grounding is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices and minimizing the risk of electrical shock and fire. By paying close attention to the details of equipment grounding and bonding, electrical professionals can create safer and more reliable electrical systems. Let's also consider the role of bonding in ensuring electrical safety. Bonding is the process of connecting metallic parts of an electrical system together to create a continuous electrical path. This path helps to equalize voltage potentials and minimize the risk of electrical shock. In parallel conductor installations, bonding is particularly important to ensure that all parallel paths are effectively grounded. The NEC requires that all metallic enclosures, raceways, and equipment be bonded together to form a continuous grounding system. This bonding must be accomplished using approved methods such as bonding jumpers, bonding bushings, and grounding clamps. It's important to ensure that all bonding connections are tight and corrosion-free to maintain a low-impedance grounding path. In addition to bonding metallic parts, it's also important to bond non-metallic parts that are likely to become energized. For example, plastic or fiberglass enclosures may need to be bonded if they contain exposed metallic parts. The bonding of non-metallic parts helps to prevent the buildup of static electricity and reduces the risk of electrical shock. Another important aspect of grounding and bonding is the use of grounding electrodes. Grounding electrodes are conductive rods, plates, or other devices that are buried in the earth to provide a connection to ground. Grounding electrodes help to stabilize the voltage of the electrical system and provide a path for fault current to dissipate into the earth. The NEC specifies the types of grounding electrodes that are permitted and the methods for installing them. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. It's important to ensure that grounding electrodes are properly installed and maintained to provide an effective grounding path. In addition to these considerations, it's also important to address the issue of stray voltage. Stray voltage is unwanted voltage that can appear on grounded surfaces, such as metallic enclosures, water pipes, and concrete floors. Stray voltage can be caused by a variety of factors, including improper grounding, unbalanced loads, and electromagnetic interference. Stray voltage can pose a significant safety hazard, as it can cause electrical shock and interfere with the operation of sensitive electronic equipment. To mitigate the risk of stray voltage, it's important to ensure that the electrical system is properly grounded and bonded. This includes using adequately sized equipment, grounding conductors, bonding all metallic parts together, and installing grounding electrodes. It's also important to address any sources of unbalanced loads or electromagnetic interference that may be contributing to stray voltage. In some cases, it may be necessary to use specialized equipment such as isolation transformers or filters to reduce stray voltage levels. In conclusion, grounding and bonding are essential components of electrical safety. By following the NEC requirements and industry best practices, electrical professionals can design and install electrical systems that minimize the risk of electrical shock, fire, and equipment damage. Remember, grounding and bonding are not just about complying with the code, they are about protecting people and property from the hazards of electricity.